Imagine a chessboard. Its alternating black and white squares represent a simple binary system. A piece is either here or it is there. This is the world of classical physics, a world of definite positions and predictable outcomes that we experience every day. But what if we look closer? What if we shrink down, past the wood grain, past the atoms, to a realm where the rules are fundamentally different? This is the quantum world. Here, the neat division of black and white dissolves. A particle can be both here and there at the same time, existing in a haze of possibilities. It's a world not of simple zeros and ones, but of quantum bits or qubits, which can be 0, 1, or both simultaneously. This is the strange and wonderful reality that governs the universe at its most fundamental level. Now consider your own mind. Think about the last decision you made. You weighed different options, explored potential futures, and held conflicting ideas in your head all at once. This internal world of deliberation feels a lot less like a classical chessboard and a lot more like that quantum realm of coexisting possibilities. The quantum mind theory invites us to consider a radical and awe-inspiring idea, that this similarity is no mere coincidence. It proposes that consciousness itself, the very essence of our subjective experience, is not just an accidental byproduct of brain chemistry. Instead, it might be an expression of the same quantum rules that choreograph the dance of subatomic particles across the cosmos. This concept challenges one of our most deeply held assumptions, the separation between our inner world and the outer universe. We tend to see our minds as isolated fortresses of thought, separate from the silent, objective reality of stars and galaxies. But the quantum mind hypothesis suggests a more profound connection. It hints that the fundamental information that constitutes the universe is not just out there, but also in here. The zeros and ones of the cosmos, the basic binary code of reality, might be the very same stuff from which our thoughts, feelings, and awareness are woven. It's a perspective that blurs the line between the observer and the observed, suggesting we are not merely spectators of the cosmic drama, but integral parts of it. As we embark on this exploration, we venture into a territory where science and philosophy meet. It's a journey that will take us from the intricate neural networks of the human brain to the deepest philosophical questions about the nature of existence. We will ask if the universe itself could possess a form of consciousness, and whether our own awareness is a localized flicker of a much larger cosmic fire. This is not a settled science with easy answers. It is a frontier of human curiosity, pushing the limits of what we know and what we can imagine. So, let's begin our journey on this cosmic chessboard, where the pieces are possibilities and the game is the very nature of reality itself. What is the universe made of? We often think of matter and energy, but some physicists propose a third, equally fundamental component: information. Think of it this way. The properties of a particle, its spin, its charge, its location, are all bits of information. The laws of physics themselves are like a cosmic algorithm, processing this information to dictate how the universe evolves from one moment to the next. From this perspective, the unfolding of space-time, the formation of galaxies, and the chemical reactions in a star's core are all part of a grand universal computation. The universe isn't just a container for things, it's an active processor of information, a story being written in the language of quantum mechanics. This idea that information is fundamental opens a fascinating door to understanding our own minds. If the universe is built on information, and our minds are processors of information, could they be two sides of the same coin? Quantum mind theories suggest precisely this. They propose that consciousness is not something the brain creates from scratch, like a factory producing a product. Instead, the brain might be more like a sophisticated antenna, a quantum receiver that tunes into and processes a universal field of information that is already present. Our individual consciousness, then, would be our unique experience of this universal information, filtered and shaped by the specific structure of our brain. This perspective recasts our relationship with the cosmos. We are no longer isolated biological machines living in a meaningless void. We are, in a very real sense, expressions of the universe's informational architecture. The same quantum principles that govern a distant quasar or a particle in a void could be the very principles that allow you to experience the color red, feel a sense of joy, or ponder your own existence. This connection isn't mystical or metaphorical. It's a hypothesis grounded in the idea that the software of the universe is also the software of the mind. The physical hardware of our brain simply provides the platform for this software to run. So when we look up at the night sky, we are not just seeing a collection of distant objects. We are seeing the vast repository of information of which we are a part. The light from a star that traveled for 1 million years to reach your eye carries information about that star's past. Our brain, a product of billions of years of cosmic evolution, processes that information and creates the experience of wonder. The quantum mind theory suggests this is not a one-way street. Our awareness, our act of observation, is an interaction with the universe's informational field, a deep and fundamental dialogue between the microcosm of the mind and the macrocosm of everything else. The idea that the mind and the universe are deeply intertwined is not entirely new. It resonates with some of the most ancient and profound philosophical traditions in human history. Long before quantum mechanics was conceived, philosophers grappled with the mind-body problem. Is the mind a separate, non-physical substance, or is it simply a product of the physical brain? One elegant answer to this puzzle is monism. Monism is the philosophical view that all of reality is ultimately made of one single substance or principle. There isn't a separate realm for mind and another for matter. They are both manifestations of the same underlying unity. This ancient idea finds a surprising and modern partner in the quantum mind hypothesis. If consciousness is a feature of the universe's fundamental information, then it supports a monistic view. The one substance is no longer some abstract spiritual essence, but could be the quantum information field itself. Mind and matter are not two different things, but two different states or expressions of this single foundational reality. The complex organization of matter in our brains allows this informational field to express itself as self-aware consciousness, while in a rock or a star, it exists in a much simpler, more rudimentary form. It's all part of the same continuous spectrum. This leads us directly to another fascinating philosophical concept, panpsychism. If consciousness is a fundamental property of the universe's information, then it might be present everywhere, in everything to varying degrees. This is the core idea of panpsychism. Not that a rock thinks like a human, but that the elementary constituents of that rock possess a very primitive, simple form of experience. A thermostat doesn't feel cold, but the information processing it performs. If temperature is below X, then activate furnace could be seen as a proto-conscious event. Panpsychism suggests that consciousness is not an all-or-nothing property that magically appears in complex brains, but is a fundamental feature of the cosmos that scales with complexity. When we look at the universe through this lens, our perspective shifts dramatically. We are not lonely islands of awareness in a dead and unfeeling cosmos. Instead, we are part of a universe that is, in some fundamental way, awake. The same proto-consciousness that might exist in the quantum fluctuations of empty space becomes amplified and refined through billions of years of evolution into the rich, subjective experience we enjoy. The quantum mind theory, therefore, provides a potential scientific framework for these age-old philosophical intuitions, suggesting that the poets and mystics who spoke of a deep connection to the universe may have been sensing a profound physical truth. If consciousness is tied to quantum processes, where in the brain might these processes be happening? This is the central question for scientists exploring the quantum mind. The brain is a warm, wet, and noisy environment, which seems hostile to the delicate quantum states that usually require extreme cold and isolation in a laboratory. This is the main reason many neuroscientists are skeptical. They argue that the brain's operations can be fully explained by classical neuroscience, the firing of neurons, the release of neurotransmitters, and the complex interplay of electrical signals. For them, consciousness is an emergent property of this classical complexity, like the wetness of water emerging from H2O molecules. However, proponents of the quantum view argue that we shouldn't dismiss the possibility so quickly. They point to specific structures within our neurons that could potentially host and protect these fragile quantum events. One of the most famous theories, known as orchestrated objective reduction or ORCH-OR, developed by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff, pinpoints structures called microtubules. These are tiny cylindrical proteins that form the cytoskeleton, or internal scaffolding of our cells, including our neurons. They are incredibly small and numerous, providing a vast potential playground for quantum computations. The Ochoa theory proposes that electrons within these microtubules can enter a state of quantum superposition, existing in multiple states at once. This quantum state is maintained for a brief period, allowing for a vast, parallel computation to occur. This process is orchestrated by the surrounding cellular structures. Eventually, this quantum state collapses into a definite classical state, a moment of objective reduction. Penrose and Hameroff daringly propose that each of these collapse events corresponds to a single moment of conscious experience, a single frame in the movie of our awareness. Billions of these events happening every second could weave together to create our rich and continuous stream of consciousness. This is a bold and highly controversial idea. A major challenge is the problem of decoherence. Quantum states are notoriously fragile. Any interaction with their environment, a stray vibration, a change in temperature, can cause them to decohere or collapse back into a classical state, losing their quantum properties. Critics argue that the warm, chaotic environment of the brain would cause decoherence far too quickly for any meaningful quantum computation related to consciousness to take place. Proponents, however, are exploring ways the brain might have evolved to shield these processes, perhaps using the unique structure of water within microtubules to create a protected quantum environment. The debate is a thrilling example of science at its edge. Let's return to the chessboard, but this time, you are the player. You are faced with a critical move. Now, your mind doesn't just evaluate one option and then the next in a linear sequence. Instead, you hold multiple possibilities in your head at the same time. You simulate the consequences of moving your knight here, your bishop there, or your rook to another square. Each potential move exists as a what-if scenario, a ghostly future that you explore without committing to any single one. In this mental space, all these possibilities coexist, each with its own potential and value. This state of holding multiple unresolved possibilities in your mind is strikingly similar to the quantum concept of superposition. In quantum mechanics, superposition is the ability of a particle to exist in multiple states or locations at once until it is measured. An electron isn't in one specific orbit or another. It exists in a cloud of probability, a superposition of all possible orbits. Only when we interact with it, when we measure it, does it choose a single definite state. The process of human decision-making seems to mirror this. Our minds entertain a superposition of choices, a mental cloud of potential actions. The moment of decision, the point where you finally commit and move your piece on the board, is like the collapse of the quantum wave function. The cloud of possibilities resolves into a single, concrete reality. This parallel has led to the development of a field called quantum cognition. This field doesn't necessarily claim that the brain is a literal quantum computer. Instead, it uses the mathematical framework of quantum mechanics as a powerful tool to model human thought, judgment, and decision-making. Researchers have found that quantum models can often predict human behavior more accurately than classical models, especially in situations involving ambiguity, uncertainty, and cognitive dissonance. For example, the way our opinion on one question can be influenced by a question we were just asked is difficult to explain with classical probability, but fits neatly into the mathematics of quantum measurement. Consider the phenomenon of cognitive dissonance, where we hold two conflicting beliefs simultaneously. This uncomfortable mental state can be thought of as a superposition of contradictory ideas. Resolving the dissonance by changing one belief or rationalizing the conflict is akin to the collapse of this superposition into a more stable classical mental state. Similarly, the way our creativity works, with ideas seeming to pop into our heads from nowhere, might be the result of a vast, unconscious quantum-like computation exploring a huge space of possibilities before one novel solution emerges into our conscious awareness. These analogies suggest that, well, the logic of the quantum world may be closer to the logic of our minds than we ever imagined. The exploration of the quantum mind is not a monolithic enterprise, but a landscape of diverse and sometimes competing ideas, championed by bold thinkers from both physics and neuroscience. The most prominent of these, as we've touched upon, is the Ochoa theory. Sir Roger Penrose, a Nobel laureate in physics renowned for his work on black holes, provides the theoretical physics foundation, arguing that our understanding of reality is incomplete without a theory that unites quantum mechanics and general relativity. He proposes that consciousness is linked to this missing piece of the puzzle, arising from the self-collapse of the quantum wave function, a process he calls objective reduction, or OR. His collaborator, Stuart Hameroff, an anesthesiologist and professor, provides the biological hypothesis for where this could happen. His deep knowledge of the brain's cellular architecture led him to the microtubules. Hameroff was intrigued by how general anesthetics work. These molecules seem to selectively erase consciousness while leaving other brain functions intact, and he found evidence that they act upon microtubules. This led him to propose that these structures are the quantum computers within our neurons, where the orchestrated, or ORCH, part of ORCH-OR takes place. Together, Penrose and Hameroff have built a comprehensive, though highly debated model of quantum consciousness. Another important area is the broader field of quantum cognition, which we've also introduced. This approach is less concerned with the biological hardware and more focused on the software of the mind. Pioneers in this field, like psychologists Jerome Busemeyer and Peter Bruser, used the mathematical formalism of quantum theory to model how people make decisions under uncertainty. They don't claim that the brain is a quantum computer, but rather that human cognition acts as if it follows quantum principles. Their work has shown that quantum probability can better explain many psychological paradoxes and biases that are difficult to account for with classical logic, providing strong circumstantial evidence that our thought processes have a quantum-like structure. Beyond these specific theories, other physicists and philosophers have contributed to the discourse. For instance, the physicist David Bohm proposed a vision of the universe with an implicate order, a deeper enfolded reality from which our perceived explicate order of space and time emerges. In his view, consciousness is a manifestation of this implicate order, suggesting a holistic connection between mind and the fabric of reality. While these theories vary in their details and the level of scientific acceptance they have garnered, they all share a common revolutionary thread. The conviction that to understand consciousness, we must look to the fundamental quantum nature of the universe itself. In the grand halls of science, every revolutionary idea must face the crucible of skepticism. The quantum mind hypothesis is no exception. In fact, it attracts a particularly intense level of scrutiny. The primary and most formidable objection, as we've noted, is the problem of decoherence. The brain is about 37 degrees Celsius. It's a bustling, soupy environment, a stark contrast to the near absolute zero temperatures and vacuum-sealed chambers where physicists normally coax quantum effects into existence. Critics, like physicist Max Tegmark, have performed calculations suggesting that any quantum coherence in microtubules would be destroyed by interactions with the surrounding environment in a matter of femtoseconds, far too short a time to be relevant for neural processes, which happen on the millisecond scale. This is a powerful argument, and it forms the bedrock of the mainstream neuroscientific view that the brain is, for all intents and purposes, a classical system. Proponents of quantum theories must provide a plausible biological mechanism by which the brain could overcome this decoherence problem. Hameroff and Penrose have proposed that the unique, ordered water within microtubules might act as a shield, but this remains a hypothesis that is difficult to test and has not yet been experimentally verified. Until a clear, demonstrable way for the brain to protect quantum states is found, skepticism will and should remain high. This is the scientific method at work. Extraordinary claims require extraordinary evidence. Another significant hurdle is the lack of direct, testable predictions that could definitively prove or disprove the theory. Science progresses by making predictions that can be experimentally verified. For example, Einstein's theory of general relativity predicted that starlight would bend around the sun, which was later observed during a solar eclipse. The ORCH-OR theory has made some predictions, such as the existence of quantum vibrations in microtubules, and some preliminary findings have been intriguing. However, linking these vibrations directly to the subjective experience of consciousness is a monumental leap that we currently lack the technology to bridge. How do you design an experiment that measures the moment of consciousness and correlates it with a quantum event? Finally, there is the philosophical objection known as the explanatory gap. Even if we discovered that quantum computations were happening in the brain, how does that explain subjective experience itself? How does a collapsing wave function create the feeling of sadness, the taste of a strawberry, or the experience of the color blue? Critics argue that simply swapping classical computation with quantum computation doesn't solve the fundamental hard problem of consciousness. It just pushes the mystery down to a deeper, more esoteric level. This is a profound challenge, reminding us that even our most advanced physics may not be sufficient to explain the inner universe of the mind without a further conceptual breakthrough. Despite the formidable challenges and the healthy skepticism, let's allow ourselves to ponder the grand implication if the quantum mind theory, in some form, turns out to be true. The consequences would be nothing short of a revolution in our understanding of ourselves and our place in the universe. The most profound shift would be the dissolution of the boundary we have long drawn between mind and matter, between self and world. We would no longer be biological accidents in an unthinking mechanical cosmos. Instead, we would be fundamental participants in a universe that is, at its core, informational and perhaps experiential. This perspective would unify the inner world of subjective experience with the outer world of objective physics. Our thoughts, our feelings, our very awareness would not be separate from the laws that govern the stars and the galaxies. They would be an expression of them. The universe would no longer be something we simply observe from the outside. It would be something we are intrinsically a part of, a system observing itself through us. This could imbue our existence with a sense of connection and belonging that transcends cultural or religious doctrines, grounding it in the very fabric of physical law. We are, in the most literal sense, woven from the same quantum cloth as the rest of reality. This shift in perspective could also reshape our approach to fields beyond physics and neuroscience. In medicine, understanding consciousness as a quantum phenomenon could open new avenues for treating mental illness or disorders of consciousness. In the field of artificial intelligence, it might suggest that creating true, subjective machine consciousness requires not just more complex classical algorithms, but a new kind of hardware capable of harnessing quantum effects. It challenges us to rethink what life and intelligence truly mean, suggesting they might not be exclusive to biological organisms, but could be potential properties of any sufficiently complex, organized system. Ultimately, the grand implication is one of unification. It suggests that the division between life and non-life, between mind and universe, is an illusion born of our limited classical perspective. Just as Copernicus moved us from the center of the universe, and Darwin connected us to the tree of all life, the quantum mind theory offers a new and potentially deeper integration. It suggests that we are not just stardust, we are the universe's way of thinking about itself. Our consciousness is a localized eddy in a vast cosmic ocean of information, a temporary beautiful pattern in the eternal quantum dance. We stand at a fascinating crossroads in our quest to understand the universe. We have charted the vast expanses of space-time and plumbed the bizarre depths of the quantum realm. Yet, the greatest mystery of all may lie within our own skulls, the nature of consciousness itself. The quantum mind hypothesis, for all its controversies and uncertainties, represents a courageous attempt to build a bridge between these two great frontiers of knowledge, the cosmos without and the cosmos within. It challenges us to be open to the possibility that the most intimate aspect of our being is connected to the most fundamental laws of reality. This journey forces us to confront the limits of our current understanding. Perhaps the reason consciousness seems so mysterious is that we are trying to explain it using a physics that is itself incomplete. Just as Newtonian physics was a brilliant approximation of reality, our current models may also be a stepping stone toward a deeper theory. A future physics that successfully unifies gravity and the quantum world might reveal that information, and even a primitive form of consciousness is as fundamental as space and time. This quest is a powerful reminder that there is always more to learn, that the universe is likely stranger and more wonderful than we can currently conceive. Whether the brain turns out to be a quantum computer or not, the very act of asking the question expands our cosmic perspective. It encourages us to see the universe not as a collection of inert objects, but as a dynamic, interconnected system in which we play an active role. It blurs the line between the observer and the observed, suggesting a participatory universe where the act of knowing is a creative engagement with reality itself. This perspective fosters a sense of humility and wonder, a recognition that we are part of something immense, intricate, and profoundly mysterious. So the next time you look up at the star-filled night sky, consider this. The light from those distant suns and the thoughts within your mind might be governed by the same deep principles. You are a part of the cosmos that has become aware. You are stardust that has evolved to ponder the stars. The quantum mind theory, in its grandest vision, tells us that the separation we feel is an illusion. We are not in the universe, we are of the universe. And our quest to understand our own consciousness is, in the end, the universe's quest to understand itself.